All right, our last data structure in this course is going to be graphs. This turns out to be a very increasingly important data structure because have you ever wondered how the GPS system in your car or your phone works to find the shortest path between 2 points on a map? This is it. This is how, this is the way, a graph is the way that maps are represented. I mean, it's the mathematical model of a physical geographical map. And the way you find, and whenever your GPS, routes your thing, that's all based on this graph theory. Now, those of you who were in, I assume everybody here has taken discrete structures, in which case you learned the mathematical definition of a graph, right? So anyway, here in figure 11.1 in part A is a picture of a graph. So what's the mathematical definition of a graph? It's a set of what and a set of what? It's two sets. It's two sets.
A set of nodes and a set.
Yeah, they're not called nodes. It starts with a V. Vertices. A vertex. A vertex is singular, vertices is plural. So it's a set of vertices. So in this particular graph on figure 11.1, what are the vertices?
0, 1, 5. Right?
Yeah, 0, 1, 2, 3, 4, 5. Okay, so that's one set, and the other one is a set of what?
It's like ordered pairs.
Well, actually, pairs is right. In this particular example, in figure 11.1, they're not ordered. They are unordered. So actually, the next one, what you ordered pairs, that makes it a directed graph. Digraph, yeah. Okay, so this is a picture of a graph, and each one. So it's a set of vertices. So how many vertices do we have? We have 6. And how many edges do we have? 1, 2, 3, 4, 5, 6, 7. When we're talking about a graph, the edges are unordered. They don't have arrowheads on the end. So this could represent like a map of a city. And each one of those lines represents a two-way road, right? Or a highway. This could be towns, cities on a county, and those could be roads, highways, connecting them, and they're two-way. All right? So that's a graph. So now, have you ever wondered, so mathematically it's a set of vertices and a set of edges, and the edges are pairs. What about that edge between 1 and 3? So the edge between 1 and 3 is represented by two numbers, the one vertex, the two vertices that the path connects. Are you with me? Now, did you ever, okay, so now that's the mathematical definition, but now, what about, have you ever wondered how in the world are we going to represent this? What data structure are we going to use to represent this inside the computer so that we can do computations on it and calculate paths? Have you ever wondered about that? Can you think of a way to do that? If you haven't seen this before?
Connected to?
Yeah, actually that's very close to the way it's done. There's two main ways of doing it. And what you came up with was the first way. This is called, now watch this. It's called an adjacency list representation. Now, what does it appear? That the data structure called graph, it looks like there's a graph sub 0, sub 1, sub 2, sub 3, sub 4, and sub 5. So that looks like a what?
Array.
It's an array. Are you with me? It's an array. Graph sub 0, graph sub 1, graph sub 2, graph sub 3, graph sub 4, graph sub 5. Are you with me? But now look. So there is a graph sub I for each what? What does graph sub 0 represent?
The 0 vertex.
The vertex 0, yeah. And graph sub 1 represents vertex 1, and so on. Are you with me?
It has all the edges
And then,
that are labeled to what it connects to.
yes. Now, in graph terminology, those are called adjacent. So you see that, do you see that in terms of the graph, vertex 3 and vertex 1 are adjacent, and vertex 1 and vertex 5 are adjacent. Now, why are they adjacent? Because there's a what?
Edge.
Because there's an edge between them. Is everybody clear on this representation? Okay? So you see, now, here's the thing. This is This is also called an undirected graph. So, and this data structure is called an adjacency list. Do you see why it's called an adjacency list? It's because you go down, if you want to know all the vertices that are adjacent to a given vertex, you go to that vertex, and then this is an array of what? Well,
vertex.
well, no, of what?
Edges.
Well, no, the data structure. It's an array of what?
Of arrays?
Nodes.
No, not of array of array. It's not an array of arrays. It's an array of, yeah, say it again. It's an array of lists. Yeah. Does everybody see what we're saying? And those lists are what? Those are just linked lists. So guess what we're going to use? List L. Yeah? Code reuse. Huh? Now do you see then that now here's the thing. You see that there's an edge between 1 and 3. So if you go to graph sub 1 and you go down that list, you find node 3, you find vertex 3, right? That means that there is an edge from 1 to 3. But then you also, if you go down to 3 and follow down the link, you'll see what?
There's an edge to 1.
Edge to 1. So you see they're both ways. I mean, each one is adjacent to the other. So now you see, hold on. So now you see that because there are 1, 2, 3, 4, 5, 6, 7 edges, there are actually how many elements total in the list of in the adjacency list?
14.
There's got to be 14. Yeah.
So you could essentially define direction with this.
Well, we're going to do that later. We're going to do that in a minute. That's called a directed graph. All right? But does everybody understand then? Is everybody clear? So if you count those up, there's 14. Now, does everybody see that, like between 2 and 5, you go down to 2 and see there's a 5, you go down to 5, you look down this and there's a 2. So that is called the adjacency list implementation of the graph. Now, that there are 2 very common representations, and this is one of them. Now, do you see, though, that if you want to find all the vertices that are adjacent to 5, you go down to 5 and you have to search through this linked list. But now, there is another representation that uses the space-time trade-off, that uses more space, but that's faster to access. If you want to know if there is an edge between vertex I and vertex j in big theta of 1, you can find it right away. Can you think of another way to store this information about a map in a different data structure?
Union statement, whether or not
Yeah, now that is exactly right. But how do you organize all the possibilities? What data structure would you use to organize all the possibilities? No? Yeah?
Matrix?
Yeah! So that's part C of the figure. You see? So this is called the adjacency matrix implementation of the graph. Now does everybody see? So now instead of just being a one-dimensional array of lists, of adjacency lists, it is a two-dimensional array, and and what is the size of the array? How many elements are in the adjacency matrix representation? It has to be it's the what?
N squared.
It's the square of the number of vertices. By the way, you guys, it's vertex and it's vertices. Like this. So this is singular and this is plural. It's always, every time people get introduced to this, it's easy to get this mixed up. All right, but anyway, do you see, now do you see then that when we looked at the edge between 1 and 3, if you go to row 1, column 3, there's a 1. Are you with me? But by the same token, if you go to row what? If you go to row 3, column 1, there's a 1. But by the same token, if you go to what? Row 1, column 3, there's a 1. Does everybody see that? And furthermore, because there's 2 entries in the matrix for each edge. So because there's 7 edges, there's how many ones? 14. Now, do you see that if the graph is if the graph is not highly connected, there's going to be a lot of zeros in there. And so if you had a map of the internet, if you had like a matrix, I mean, it'd be humongous. Right? And most of them would be zeros, because how many connections does each internet, does each node in an internet, if we're talking about a map of the internet, modeling a map of the internet, then most of those would all be zeros. So this is very space hungry. I mean, but it's very fast. Yeah.
If it's not directed, couldn't you just cut the entire thing by half?
That is a good point. That is a good point, and the answer is yes. So your observation is, because you see, that was the next thing I was going to point out. What property does this matrix have? It's symmetric about the diagonal. So theoretically, you only need half of that. So you could slice it off and just use half, yeah. And then you would look up the index of the row. You would see if the row or the column is bigger and look up whichever one, yeah. Yeah, but that would cut it in half. Still order n squared, though. 1/2 of n squared is still n squared. But that was a good observation. Now, does everybody see how this works? Now, the other thing that you learned in discrete structures is what a directed graph is. So in a directed graph, the edges are ordered. Okay? So now, what is the mathematical definition of a directed graph? It's a set of edges. Now, it's a set of edges and it's a set of vertices. And then for the edges, it's a set of what? Now, it's ordered pairs, because it's the from to, because now the direction matters. But look, don't you see that now with a directed graph, what 2 representations do we have? Same ones. Are you with me? So look here. This is the adjacency list implementation of the diagraph. Oh, by the way, directed graph, abbreviated as digraph. Okay? So this is the adjacency list implementation of the digraph. And now it's just like the other one, only now, what is the interpretation of the fact that graph sub 2 has a 4 in the adjacency list? The 2 is which vertex? The from vertex or the to vertex? It's the from vertex. And then the 4 is the to vertex. So it's from 2 to 4. Yeah? But look, in terms of the code, in terms of the data structure, it's the same thing. The only thing is, with a digraph, you're not what's the restriction with a graph? For every what? For every edge in a graph, there's a what? For every edge in the graph, there's two entry. There's two entries for the edge, and it's symmetric. If there's an edge from I to J, then there's one from J to I. So it's the only restriction is that they get installed and removed as pairs, whereas with a digraph, they can be installed and removed just as individuals. So in our software, we're going to make a distinction between graphs and digraphs. And if it's a graph, we'll do a little demo here in a minute. And if it's a graph, then the user will just specify an edge. And when we put in an edge, we'll put in the from to and also the to from. And when we remove, we'll have to remove the from to and the to from. See? But with the digraph, we can do them individually. But other than that, the algorithms are the same. Except for just the way that it's maintained. You see what I'm saying? The difference between graph and digraph is how they're maintained. And so now look, here is the adjacency matrix implementation. So the fact that there is an edge from 2 to 4, that means row 2, column 4 has a 1 in it. Does everybody see that? From 2 to 4 means the graph, row 2, column 4 has a 1. And now the matrix is not what? Not necessarily what? It's not necessarily symmetric. So now you can't cut it in half. Use that little trick. Yeah? Are we good? Okay, so now with that in mind, let's do a little demo and see how the software works. I tell you what, let's do. Let's build this graph.
So,
in our demo. Let's build this graph in our demo. Now here, maybe I'm going to answer your question. Let's build this graph in it. Now here's the thing. The order in which those elements are in the adjacency list is unimportant. That means that there is more than one way that the data structure can be, that the data can be listed in there for the same graph. In other words, it doesn't matter if you have a, if graph sub 1 had the list 5430 and 5304, that would be the same graph. So the order is irrelevant. But now the way we're going to build it, let me see. By the way, do you notice the way these numbers are printed out? Do you notice the order that they're in here on this graph?
high to low.
Yeah, high to low. So what we're going to do is, so here what let's do is, let's enter the edges 0, let's enter the edges from 0 to 1, and then 1 to 3, 1 to 4, 1 to 5. Sorry, 1 to 0, 1 to 3, 1 to 4, 1 to 5. And then, so, because when it gets put in, it gets pre-printed. See? So let's try to build this.
So in reverse order.
Okay, so here's our demo. The project is the graph project. So let's run this. And now look how the software works here. It asks if it's a digraph right off the bat. So there's going to be an attribute for each graph saying whether it's a digraph or not. But the only thing it's going to do is when you do the insertions and deletions, if it's a digraph, it's going to allow one edge at a time, and if it's not a digraph, it's going to put them in and remove them in pairs to maintain that invariant. Okay, so let's say it's not a digraph. And by the way, the other thing that it does is it asks for the number of vertices, and that's fixed throughout the whole thing. So you can add and remove edges, but you can't add and remove vertices.
Oh,
Yeah.
how come?
Well, because that would be more complicated. But I mean, usually, like in a map, the towns are fixed, or in an airline, in an airline, the cities are fixed. The question is, do you add a route or not? So it's even a reasonable, realistic one. Okay, so number of vertices, we'll say 6. All right. Now check this out. If we do a right W. Now, unfortunately, what this does is I don't. Can you imagine? But it would be like if we graphically were able to draw a graph instead of, with the vertices and the edges. I mean, that's a little. I mean, it's possible. It's doable. It happens. Actually, that would make a nice little project. If some of you guys want a little text output, so because this isn't graphical user interface, but there's algorithms to do all that kind of stuff. But anyway, we're just going to show the adjacency list. Okay, so now what do we have to do? From 0 to what?
1.
So let's insert 0 to 1. All right, but now the only thing that we have to show for all of our work here is this. But there's more. So if we go back to our slide, so basically what we've done is we have shown how to input this data structure that represents this graph. What else can we do? Okay, we're going to introduce the well, I'll demo it now, but you know how in a binary tree there are 2 ways to visit each node in a binary tree? No, sorry, there's 3 ways. What are the 3 ways that you can visit each vertex in a binary tree?
In order, post order.
Yeah, pre-order, in order, and post order. But these aren't trees, these are graphs. So what do you think? What are the ways to visit?
There's 2.
There's 2.
2 to from to 2.
No. These 2 ways of visiting each vertex in a graph are called breadth first search and depth first search. Those are the 2 ways to visit. Now, so let's demo that. So now here, you see, here back in our demo, we have a breadth first and a depth first. So let's do a breadth first. Now when we do a breadth first search, it tells us which vertex. You can start from any vertex. It's not just the root. There is no root vertex. You see? So if we start from 0, what is the breadth first search? Look what it is. It's 015432. Are you with me? And then there is some additional information that's printed out here. The discovered time, the finished time for each vertex, the predecessor vertex, and the distance. So we'll see what all those mean here in a minute. But you can start from another vertex. So actually, let's go back to our picture. 015432. Let's go back. So you see what did it do? It went 01543 and then 2. That's interesting. Why did it do that? We'll see here in a minute. But you can start from any other vertex. Suppose you started at vertex 5. What do you suppose? So let's do a breadth first search. Start vertex at 5. What is it now? 542130. Let's look at the picture. See what it's. Oh, look, it's 5 and then the 4 and then the 2. Now, do you see what it's doing? It's kind of like fanning out. It's breadth first. So 5, 4, 2. And then what were the next ones?
1, 3.
1 and 3 next. And then what? 0 last. Yeah, we'll see. We'll see. we're going to look at the algorithm. There's an algorithm that you are going to implement. You are going to implement the algorithm, actually. I'll give you the pseudocode and you'll implement it. Okay, so that's the depth first search. Now what about, a breadth first search. Now you can also do a depth first search. So now let's do a depth first search starting from 3. So let's do a depth first search starting from 3 and see what it does. So now what does this do? 345210. So it did 3, 4, look, it did 3, 4, 5, 2. It got as far as it could. Depth. See? It got as deep as it could until it finally had to do what? Back up. 3, 4, 5, 2. Then backed up and did 1, 0. And then it backed up to 3. So that's a depth first search. So we're going to do some detailed traces of this in a minute. But anyway, those are two things. Now one more thing. Here, let's remove, check this out you guys. If we remove the edges between what? 1 and 5 and 4 and 5. Are you with me? What will happen to this graph? There'll be two islands. All right? And the one island will be 0, 1, 3, and 4, and the other island will be 2 and 5, right? So let's remove the edge between 1 and 5 and 4 and 5. Now watch. So now let's remove edge. R from vertex, what did we say?
1, 5.
1. And the other one was what?
4, 5.
4 and 5. Now let's write it. There you see, there's the adjacency list. But now what do you suppose is going to happen if we do a breadth first search starting at 1? So let's do a breadth first search starting at 0. Is that what we did before?
No, we started at 3.
Well, anyway. Yeah, okay, so anyway, we'll start at 3. And so now what's going to happen? Just 3, 4, 1, 0. It couldn't get to the 2 or the 5. See? Because they're disconnected. There's no way to visit. You can have islands. Those are called components. Each island is called a connected component. Do you remember that from your discrete structures? All right. And notice that whenever we deleted one edge, it deleted both. Here, if we write this, it deleted both pairs of nodes from the adjacency list. Did everybody see that? All right. Let's end this demo. Oh, and then we could do the same thing with a directed graph, but let's end it.
What if you did components?
Oh, good. Oh, that's an excellent one. Let's do components. There are 2 connected components. Check that out. You're going to program that too. Yeah, in fact, I'm glad you mentioned that because that was my point of making those connected components. I mean, of disconnecting them and making them. Now, do you want to put an edge back in?
Sure.
And what if we put an edge from what to what? Can we make these connected? Oh, anyone between 0 and 4 and 3 and 2 and 5. What do you want to put? Let's insert an edge between 4 and 5. And now let's do components. There's one connected component. Yeah, what about, oh, edges. Yeah, let's demo edges. Good point. It just says how many edges there are. All right, and now look, you notice here that if we write, there's actually 6 edges, but how many items there are total in the lists? 12. Right? Does everybody see that?
Okay.
There's 12 items in the list because you got it each way, right? Because this is not a digraph. And here, shall we do, yeah, let's do path. Path from 0 to what? Isn't there one from 0 to 2 direct? Oh, are 0 and 2 adjacent? Oh, no, they're not. That's a good one. It gives us a breadth first, it does, here's the answer to your question. It does a breadth first search. It says the path from 0 to 2 is 0, 1, 4, 5, 2, and the distance is 4. So 0 to 1, 1 to 4, 4 to 5, and 5 to 2. So there's 4 links. It does all that.
That is the shortest path.
And it's the shortest one. Yes, we're going to see how all that works. Okay, so that's the demo. Now, now let's take a look at the code. And so we are using the adjacency matrix, we are using the adjacency list representation as opposed to the adjacency matrix. Now check out these attributes, you guys. First of all, we have an enum. Have we done enumerated types in here before? You know what enums are? Maybe we haven't. Do you, no, well, red black was Boolean. That was true false. You remember? Yeah, these are enumerated types. Anyway, well, now's a good time to
learn.
Yeah. Okay, so it's a with enum, what you do is you name. It's when you have discrete values and you want to give each value a name. So it's for internal documentation. Basically, what this enum color type is, it's as if white was an integer 0 value, and gray was an integer 1 value, and black is an integer 2 value. That's basically what it is underneath the surface. So the C++ coding convention is for enums to be all uppercase. We have typedef, struct, and then what is its name? Typedef, struct, and then we have the brace, and then what is the name of the struct? Graph vertex. So you see, that is the name of our struct. So what is a struct? A struct is just like a class, only it usually just, instead of using it like a class, we typically only use it when it has just attributes and no methods. Do you see what I mean? So those are like attributes of a class. And so now, how many attributes does this struct have? 1, 2, 3, 4. It has how many? Yes, 5.
Is color type something that's like already defined? Like,
okay, good point.
oh, that's our thing.
That's our, yeah. So you see, color is the name of the attribute, and its type is color type. So what are the values that the color attribute can have? It can be either what? White, gray, or black.
Okay, yes.
Okay, and now we have these next four attributes are integers. So we have an integer discovered, integer finished, integer distance, and integer predecessor. Now each one of these is used, in fact all of these items in the struct are used for, some of them are used to trace, for tracing purposes, just so that we can, when we trace through these algorithms. And discovered, let me just mention what each one is. Whenever you do a search, you know, there's a depth first search and a breadth first search. Whenever you do a search, discovered is the time at which it's discovered. So time is going to be, actually, you see time here in class graph is an int underscore time. And so each time we go through a step in a search, we're going to increment time by 1. And then discovered is going to be the time that the vertex is discovered. And then finished is going to be the time that the algorithm is finished with that vertex. Do you see what I mean? Distance is going to be the distance of the path between that vertex and the starting vertex. And the predecessor is going to be the vertex that preceded that one in the search. That's what the meaning of those are. Yeah. Yeah, okay, yeah. So now let's take a look at class graph. And so we have an int, and yeah, and we'll see that right down here. So, so we have an int num vertices. Now you know what that is. The program asked us for that at the beginning. How many vertices? It was 6 in our example. Bool is digraph. It asks us whether it's a digraph or not. You with me? Int time, that's the time that's going to be for our algorithms so that we can trace through, see the trace through of our algorithms. And now look, we have, what's our first array? It is an array, it's called underscore what? Our first array T is called underscore what?
Vertex.
Vertex. That is an array of what? Graph vertex. So each one of those is a what? A graph, each one of those has 1, 2, 3, has 5 things in it. Each vertex has those 5. Is everybody clear on that? You have one array to store all that stuff for each vertex. But now what about the graph itself? What about underscore graph itself? What is it? It is an array T of what? List L of what? Lists of ints. That is the adjacency list representation. It is an array of lists. Does everybody see that? And furthermore, to process, to go down that list, we're going to use list L. But how are we going to access the individual members of list L? We are going to use the what pattern? Iterator. This is why we set up the iterator for the list L. So we could use it, list L, because what we have to do is we have to go down those, to do all this processing, we have to go down the adjacency list and get the data from each one. But how are we going to do that? Well, we use this list editor. So what do we have? This array T, so the name is graph iter, and what is it? What is it? It's an array of list iterators of ints. So we'll have to review how that works, how the iterator works. You probably might have forgotten that. But you see that's the reason if we didn't have that iterator, then we'd have to set up our own linked list. We'd have to program our own linked list for the adjacency node. We want to reuse what we already had. Yeah, that's a good question. Because there's 2 different arrays, and each one of them is an array, and the size of each array is the size is the number of vertices.
Right.
And so if we go so if we go back to here to this adjacency list, you can imagine called graph. There's another one called vertex. And instead of being an array of lists, it's just an array of each one of those 5 things. Information at each one of those 5 things in a node. Do you see how that is? And so they're kind of like, these are called parallel arrays. Okay. They're parallel arrays. Yeah. Yeah, are we good? Okay, so we'll take this up tomorrow. It looks like we're going to have to postpone your assignment. I mean, because it's due tomorrow, right? Yeah. Yeah, well, we'll make it Thursday or whatever.